Hello and welcome to our second lecture about the geometry of space. Today is the 5th of November, so let me wish you a happy Guy Fawkes night. Today we're going to be talking about the cross product. Last week we talked about the dot product. The cross product is another way to combine two vectors. And then we'll be talking about lines and planes in space. First, let's talk about the cross product. Now, before we go on, we're going to need to use our left hand again. Imagine holding your left hand up, like in the picture. The second finger will point in the direction U, and the first finger will point in the direction V. And then our thumb will tell us a direction, which we're going to call N. So more precisely, let N be a unit vector which satisfies three rules. We want N to be orthogonal to U. That means that the angle between N and U will be 90 degrees. We want N to be orthogonal to V. That means that the angle between N and V needs to be 90 degrees. And then we want to choose the direction of N using the left-hand rule. Second finger pointing in the direction U, hold your first finger pointing in the direction V, rotate your hand, and then your thumb will give you the direction N. The cross product of U and V is then defined using this formula. U cross V is the norm of U multiplied by the norm of V multiplied by sine theta multiplied by the unit vector N. This is similar to a formula that we had last time for the dot product. Last time we had U dot V was norm of U, norm of V, and then cos theta, where theta is the angle between the two vectors. It's almost the same thing, except now we're multiplying by a vector N, and now we're using sine instead of cos. Key thing to note here is that U dot V is a number, but U cross V is a vector. If U and V are parallel, that means either the angle between them is 0 or the angle between them is 180 degrees. Then we must have the sine of theta is 0, because sine of 0 is 0, sine of 180 is 0. So in our formula at the top, if sine is equal to 0, then U cross V is equal to 0. Let me quickly run through some properties of the cross product. In these properties, U, V, and W will be vectors, R and S will be numbers. Property 1, RU cross SV is the same as RSU cross V. If we have two vectors and some numbers, it doesn't matter where we put the numbers in. They can be multiplied by the vectors, or they can take them out, factor them out, and multiply them at the end. Doesn't matter. Property 2, another straightforward one. U cross V plus W is the same as U cross V plus U cross W. Okay. V cross U is the same as minus U cross V. I'll come back to that one in a moment. Property 4 is almost the same as property 2. V cross W cross V plus W cross U is the same as V cross U plus W cross U. We could combine number 2 and number 3 together to make number 4. Zero vector cross U is equal to the zero vector. Think back to the formula for the cross product. That included the norm of u and the norm of v. Well, if one of our vectors is 0, it has 0 norms, the whole thing must be 0. This bold u is not the number 0, this is the 0 vector. And the final one, which is perhaps not obvious, but it's one we need to learn, u cross, open bracket, v cross w is the same as u dot w multiplied by v minus u dot v multiplied by w. We just explain why it makes sense. Not that it's true, but it makes sense. V cross w is a vector, and then we do u cross a vector. That's okay, we can do that. On the right-hand side, u dot w, that's vector dot vector. That's a number. And then we have number multiplied by a vector, which gives a vector. And the same, u dot v w, that's number multiplied by a vector or vector. Both sides of this equation are vectors. Let's go back to property 3. Property 3 said that v cross u was equal to minus u cross v. Remember, we decide the direction of the cross product of a vector using our left hand. If I'm using the left picture, if I'm going to do u cross v, I put my second finger on the direction u, I turn my hand so that the first finger points in the direction v, and then my thumb tells me that u cross v must point upwards. Now let's look at the right picture. On the right picture, I want to do v cross u. So in the right picture, I need to turn my hand so now my second finger is pointing in the direction v, and my first finger is pointing in the direction u. And then my thumb gives me the direction v cross u, which must be pointing downwards in this picture. V cross u and u cross v are both vectors. They're both vectors of the same size. They have the same norm, but they point in opposite directions. So one is equal to minus the other one. Let's talk about the area of a parallelogram. Think about, we have two vectors u and v with the same initial point, and then we sketched out this parallelogram. The area of the parallelogram is the base multiplied by the height. The base is the norm of u, that's straightforward, but what's the height? From this picture, we can see that the height must be the same as norm of v sine theta. There we get norm of u, norm of v sine theta. That's almost what we have at the top. At the top, we can see that u cross v is norm of u, norm of v sine theta multiplied by the unit vector n. Take the norm of the thing at the top, and we get exactly norm u, norm v sine theta. So the area of a parallelogram is norm u cross v. Area of a triangle. The area of this triangle is half of the area of the parallelogram that we just did. So the area of this triangle must be a half u cross v. Sorry, a half norm of u cross v. I'll show you some examples of area of triangle later. But first, we should find a formula for u cross v. Let me remind you of the three standard unit vectors in R3. I is the vector 1, 0, 0, j is the vector 0, 1, 0, and k is the vector 0, 0, 1. What do we get if we do I cross I? By the definition, we get norm of I, and then norm of I, sine of 0, and then a unit vector n. But wait a minute, sine of 0 is just 0. So I cross I must be the 0 vector. For the same reason, j cross j must be the zero vector and k cross k must be the zero vector. What about if I wanted to do I cross j? Look at this picture. Hold your hand up in front of the screen and rotate your hand so that your second finger points in the direction I and your first finger points in the direction j. Where does your thumb point? Your thumb points in the direction k. So I cross j must point in the same direction as k. So I cross j must be norm of I, norm of j, sine 90 degrees, and then our unit vector is k. But I is a unit vector, so norm of I is just 1. J is a normal vector, so the norm of j is 1. What is sine 90 degrees? Sine 90 degrees is also 1. So we end up with just k. I cross j is equal to k. Then straight away we can say that j cross I is minus I cross j, or minus k. For the other 4, I'm going to leave it for you to check. When you rewatch this lecture or when you look through these lecture slides, hold your hand up in front of this picture, rotate your hand so that your second finger is pointing in the direction of the first vector and your first finger is pointing in the direction of the second vector, and then see where does your thumb point. I'm going to leave it for you to check that j cross k is I, k cross j is minus I cross k is minus j, and k cross I is j. Okay. Now let's suppose we take any vectors, u and v. I want to take the cross product of these two vectors. I have u1i plus u2j plus u3k cross v1i plus v2j plus v3k. And we can multiply these out in the same way that we would if they were just numbers. We can multiply the first two together. We would get u1 v1 I cross I. And then we would do first one and second one. u1 v2 I cross j. First one and third one. u1 v3 I cross k, etc. We would have 3 multiplied by 3, or 9 terms. And here they are. Here's all 9 terms. First one cross first one, that's u1 v1, I cross I. And then first one cross second one, u1 v2, I cross j, etc. We end up with 9 terms. But a lot of these we can simplify. Some of these are going to be 0. Here's the table that of results we just did. Remember, I cross I is 0, so we can forget about this. J cross j is 0, so this one is 0. K cross k is 0, forget about this. And then we can use the table. I cross j, here it is, that must be k. I cross k, look in the table, that's minus j, and so on. We get 0 vector plus u1 v2k minus u1 v3j, and so on. Let's group together the I terms, the j terms, and the k terms. The formula for u cross v is this. u2 v3 minus u3 v2i minus u1 v3 minus u3 v1j plus u1 v2 minus u2 v1k. Because this is an important formula, I'm going to write this as a theorem. This is a formula for U cross V. Now, some of you will have studied matrices and determinants in high school. At this university, we don't teach them until Mathematics 3. So some of you will know about matrices already, some of you may not. If you already know about matrices, then you may want to use this formula for U cross V. If you don't already know about matrices and determinants, then I recommend you use the one that I gave on the previous slide. I'm going to write this formula at the top of the few slides because we're going to be using this formula. For example, find U cross V and V cross U if U is the vector 2i plus j plus k and V is the vector minus 4i plus 3j plus k. We need to use the formula at the top. First, we want U2 multiplied by V3. U2 is 1 and V3 is 1. So that's 1 multiplied by 1. And then we want U3 multiplied by V2. U3 is 1 and V2 is 3. So we have minus 3 multiplied by I. In the start of the next bracket, I want U1 V3. U1 is 2 and V3 is 1. So I have 2 just here. And then it's minus U3 V1. U3 is 1 and V1 is minus 4. 1 multiplied by minus 4 is minus 4. So it's 2 minus minus 4. The fifth number is U1 V2. U1 is 2 and V2 is 3. 2 multiplied by 3 gives us 6. And then the sixth number is U2 V1. U2 is 1 and V1 is minus 4. So we get minus 4 here. Simplify that, that's minus 2i minus 6j plus 10k. And we're also asked to find V cross U, but that's easy because V cross U is just minus U cross V. So that must be just 2i plus 6j minus 10k. Next example. Find a vector which is perpendicular to the plane containing the points P, Q, and R. Now we could find vectors in the plane easily. We could find the vector from P to Q, we could find the vector from P to R. How could we find a vector which is perpendicular to both of those vectors? We could take the cross product. We want the vector PQ cross PR because PQ cross PR is orthogonal to PQ by definition, and it's orthogonal to PR. If it's orthogonal to both of these vectors, then it must also be perpendicular to the plane. So let's do the calculation. We can calculate PQ, that's Q minus P, and we can calculate PR, or R minus P. And then we can do the cross product of these two vectors. I'm going to be deliberately quick here. I'm going to leave this for you to check, rewatch the lecture, or read through the slides and check that you're happy with this calculation. Please check that the answer is 6i plus 6k. Find the area of triangle PQR, where PQ and R are the same points that we used in the previous example. We have a formula for the area of a triangle. The area of a triangle is a half multiplied by the norm of PQ cross PR. And we already know PQ cross PR. In the previous example, we found that that's 6i plus 6k. So the area of this triangle must be a half multiplied by the norm of 6i plus 6k. And I leave it for you to check that that's 3 root 2. And this is the way to give the answer. You don't need to use a calculator. You don't need to type root 2 into a calculator to get a number. For a maths course like this, we want answers like this. Just give 3 root 2 if you're answering this question. Find a unit vector perpendicular to the plane containing P, Q, and R, where P, Q, and R, again, are the same points as before. We talked about how to find a unit vector in the same direction as the vector last week. We already know that PQ cross PR is perpendicular to the plane. We just need to normalize this vector to find a unit vector. In other words, we just need to find a unit vector which points in the same direction as PQ cross PR. So all we do is we do PQ cross PR divided by the norm of PQ cross PR. And we've done most of the work before. PQ cross PR we know is 6i plus 6k. In the previous example, we calculated the norm of PQ cross PR, which was 6 root 2. So the answer here must be 1 over root 2i plus 1 over root 2k. Here's an example which I don't think is in the textbook, but it's an interesting example. A triangle is inscribed or drawn inside a cube of side 2, as shown in this picture. Use the cross product to find the area of the triangle. Now, be careful if you're given a question like this. If you're told to use a particular method, then you have to use that method. If you answer this question using a different method, then you would get 0 points, even if you correctly found the area of the triangle. This question says we must use the cross product. So how do we do this? We know that the area of a triangle is a half u cross v if we know 2 vectors. But how do we get 2 vectors from here? The first thing to do is to draw some coordinate axes and assign coordinates to the vertices of the triangle. We could put the origin anywhere we want. It doesn't matter where we put it. I choose to put the origin of our coordinate system on the back corner of the cube. But you don't have to do that. You could put the origin anywhere you want. And then I can see coordinates for the 3 corners of the triangle. This corner, corner A, must be at 2, 0, 0. Corner B must be at 2, 2, 0. And corner C must be at 0, 0, 2. Then what we're going to do is we're going to take 2 vectors. I'm going to choose the vector AB and the vector AC. I'm going to take the cross product of these 2 vectors, calculate the norm of their cross product, and then divide by 2 to get the area of this triangle. So first of all, the vector from A to B, please check, is 2j. The vector from A to C, please check, is minus 2i plus 2k. We can calculate the cross product of these 2 vectors. If you understand determinants, use this notation. If you don't understand about determinants, you can use the formula that I've been using before. I multiplied by 4 minus 0 minus j multiplied by 0 minus 0 plus k multiplied by 0 minus 4, which is 4i plus 4k. Therefore, the area of this triangle is a half multiplied by the norm of AB cross AC. And I'm not going to talk about the details here. I'll leave it for you to check that this is equal to 2 square root of 2. One final idea for this chapter. The idea is the triple scalar product as a way of combining the cross product and the dot product. The triple scalar product of u, v, and w, and the order is important. It's u first, then v, and then w final. That's u cross v dot w. Now, u and v are vectors. U cross v is a vector. W is a vector, so we're doing vector dot vector, and that gives us a number or a scalar. The triple scalar product of u, v, and w is a number. What could we use that for? We could use that for the volume of a parallelepiped. This three-dimensional object is called a parallelepiped. And let's work out the volume. The volume will be the area of the base multiplied by the height. Area of the base, that's easy. The area of the base is an area of a parallelogram. We've talked about that, and that's norm of u cross v. For the height, we use a little bit of trigonometry. The height must be norm of w cos theta, where theta is the angle between w and u cross v. But of course, that's just the same as the absolute value of u cross v dot w. It's the absolute value of the scalar product of u, v, and w. I'm not going to do any examples using that formula. It's there if you need it. But I do want to make one final comment in this chapter. We can do the dot product in both R2 and R3. But we can only do the cross product in R3. There's no cross product in R2. Why is that? Because we have to use our left hand to define or to decide the direction of u cross v. If we're only in two dimensions, we can't use our three-dimensional hand. Final chapter for today's lesson is lines and planes in space. To describe a line in R3, we need two things. We need a point that the line passes through, point P0, and we need a vector which gives us the direction of the line. So if R0 is the vector from the origin to P0 and R is the vector from the origin to P, we could say that R is R0 plus some multiple of V. Or in terms of coordinates, that's the same as saying a point x, y, z on the line must be equal to the point x0, y0, z0, which we know is on the line, plus a multiple of the vector which is parallel to the line, plus t, v1, v2, v3. Or we could split that up into three different equations. X is equal to x0 plus tv1, y is equal to y0 plus tv2, and z is equal to z0 plus tv3. And it's these equations which we're going to be using. These are called the parametric equations for the line L, which passes through the point P0 parallel to the vector V. X is equal to x0 plus tv1, y is equal to y0 plus tv2, and z is equal to z0 plus tv3. For example, find parametric equations for the line passing through the point P0 parallel to the vector V. This we can do straight away. For P0, we use that for the first numbers. -2, 0, and 4. Put -2 in the first equation, we put 0 in the second equation, and we put 4 in the third equation. From V, the numbers are 2, 4, and -2. 2, we put in the first equation, 4, we put in the second equation, and -2, we put in the third equation. So the answer to this question, the three equations, are x is equal to -2 plus 2t, y is equal to 0 plus 4t, or just 4t, and z is equal to 4 minus 2t. That's all we need to do. I can show you a picture of this line. This blue line is the line L. It passes through the point -2, 0, 4. Passes through there when t is equal to 0. When t is equal to 1, the point is just here. When t is equal to a half is there, t is equal to 3 over 2, and so on. T is equal to minus a half. We can have a point over here, and so on. You can see from this picture that the line is parallel to the vector v. Next example. Find parametric equations for the line passing through the point P and the point Q. Slightly different equation, slightly differently phrased example. We need a point on the line, but we have two. We can choose either one that we want. It doesn't matter which one we choose. I'm going to choose to use P, but it really doesn't matter. And we need a vector which is parallel to the line. And I'm choosing to use the vector from P to Q. And then we have enough information to write down the parametric equations. From the point, we get the first numbers. First number of the x equation is -3. And from the vector, we get the second number. We get x is -3 plus 4t. And for the same reason, v is 2 minus 3t, and z is -3 plus 7t. Now, previously, we let t be any number between -infinity and infinity. Let's suppose we don't want to do that. Let's suppose we don't want a line which goes to infinity in each direction. Let's suppose we just want a part of a line or a line segment. Then we can restrict t to be between two numbers. For example, parameterize, that's another way of saying find the parametric equations. The line segment joining the point P and the point Q. This is the same point P and the same point Q from the previous example. So we already know the x, y, and z equations. We just need to find the bounds that we allow t. What values of t are we going to allow? Now we can see that the line passes through the point P when t is equal to 0. Replace t by 0 in these equations, and we get minus 3 to minus 3. We get the point P. And we can see that if we put t equal to 1 here, it's 1 because we use the vector from P to Q, then we get minus 3 plus 4, or 1, 2 minus 3, minus 1, minus 3 plus 7, or 4. So if t is equal to 1, we get Q. Therefore, we must allow t to be between 0 and 1. And here is a picture of this line segment. Let's take an example from the book. A helicopter is to fly directly from a helipad at the origin in the direction of the point 111 at a speed of 60 meters per second. What is the position of the helicopter after 10 seconds? Okay, so we're going to be starting at the origin, and then it's going to be flying in the same direction as 111. The first thing we want is a unit vector which points in the same direction as 111. We know how to do that. So then the position of the helicopter, let's call it RT, must be the origin plus t multiplied by the speed, 60 degrees, multiplied by the direction. Multiply these together, we get 20 root 3t, I plus j plus k. And then the question says, what is the position after 10 seconds? We can calculate that that must be 200 root 3, 200 root 3, 200 root 3. Can you hear me now? Okay, let me go back to here and I'll repeat it from here. I want to find the distance from a point S to a line L. And I'm interested in the shortest possible distance. So I'm interested in the distance of the line when this angle is 90 degrees. What is this distance? We can see from this picture that this distance must be norm of PS multiplied by sine theta. But that looks like the formula for PS cross B. Both equations have norm of PS in. Both equations have sine of theta in. The second equation has n in, but that's a unit vector. And remember, the norm of a unit vector is always equal to 1. So that will disappear when we take the norm. Combining these together, we get the formula that we're going to be using. The distance from the point S to the line L, that's the line passing through the point P, parallel to the vector V, is norm of PS cross V divided by norm of V. Find the distance from the point 115 to the line x is equal to 1 plus t, y is equal to 3 minus t, z is equal to 2t. We need a point on the line. That's easy. We can just set t to be equal to 0, and we can see that the point must be 1, 3, and 0. And we also need a vector which is parallel to the line. Again, that's easy. We'll just look at the numbers in front of the t. Plus 1, minus 1, 2. The vector I minus j plus 2k must be parallel to the line. We're going to need PS and PS cross V. I leave these for you to check. And then we use our formula, the norm of PS cross V divided by norm of V. And again, I leave this for you to check. That comes out to be the square root of 5. And that's a good place for us to take a break. Please relax for 14 minutes and then we will continue the lesson at 2 o'clock. Now let's continue. The next topic I want to talk about is intersecting lines. And I wrote this is not in the book. It actually is. It's hidden away in the problem section. They don't have the theory about this. Suppose we have two lines, and when do they intersect at a point P? They intersect at a point P if and only if we can say that the point P lies on both lines. So, for example, do the following two lines intersect? And if the answer is yes, where do they intersect? The first line is x is 7 minus t, y is 3 plus 3t, and z is equal to 2t. Because I've already used the letter t, I need a different letter for the second line, so I'm going to use the letter s for the second line. Second line is x is equal to minus 1 plus 2s, y is equal to 3s, z is equal to 1 plus s. Now, two lines intersect if and only if we can find a point which is on both lines. In other words, they intersect if and only if there exist numbers s and t such that these two lines are the same. 7 minus t is the same as minus 1 plus 2s. And 3 plus 3t is the same as 3s. And 2t is equal to 1 plus s. Now, just to repeat that, or to be more precise, we need to be able to find a number s and a number t which works for all three lines at the same time. Let's play around with this. Let's take the first equation first of all. Rearrange the first equation. We see that t must be the same as 8 minus 2s. And the second line tells us that s must be the same as t plus 1. Let's combine these two together. Putting t is equal to 8 minus 2s into the second line, into s is equal to t plus 1, we see that s must be the same as 9 minus 2s. And then we find that s must be 3 and t must be equal to 2. Now, be careful here. If we use s is 3 and t is 2, then we know that the first line is true and we know that the second line is true. But what about the third one? The two lines intersect only if all three lines are all true. We need to check the third equation. If we use s is 3 and t is equal to 2, from the third equation, 2t is the same as 2 minus 2 or 4. That's the same as 1 plus 3 or 1 plus s. So yes. The third line is also true if we use s is 3 and t is equal to 2. That tells us that the two lines intersect when s is 3, when t is equal to 2. In other words, they intersect at the point 5, 9, 4. How did I get this? Either take the first equation and replace t by 2, so it's 7 minus 2, 3 plus 6, and 4. Or we could take the second line and we could replace s by 3. Minus 1 plus 6, 3 multiplied by 3, or 1 plus 3. 5, 9, 4. Another example. Do these two lines intersect? And if the answer is yes, where do they intersect? So that's the same as saying, can we find s and t such that these three equations are all true? Let's start at the second one. That's the most straightforward. The second line tells us that s and t must be the same. If s and t are the same, then the first line becomes 2 plus t is equal to 2t, so t must be 2. However, if s is equal to t, then the third line becomes 2 plus 2t is equal to 0, or t is equal to minus 2. It's not possible to find an s and a t such that all three equations are true at the same time. Hence, these two lines do not intersect. I want to talk about the distance between two lines. And there's three cases to consider. Case one, maybe the two lines intersect. Well, that's the easiest one. If the two lines intersect, then the distance between them must be 0. Maybe the two lines are parallel. If they're parallel, then what is the distance between them? Or maybe the lines do not intersect and they're skew. They do not intersect and they are not parallel. Then what is the distance between the two lines? So as I said before, if the lines intersect, that's easy. Clearly the distance between intersecting lines is 0. We don't need to talk about this. Parallel lines. Now remember, the lines are parallel if the vectors are parallel. And parallel vectors, if they're non-zero vectors, means that their cross product must be the 0 vector. This is the case we have when v1 cross v2 is the 0 vector. Now, we can see from this picture that the distance between two parallel lines is the same as the distance between a point P2 on line 2 and the distance between P2 and the line L1. We already have a formula for the distance between a point and a line, so we'll just adapt that. The distance between parallel lines will be the norm of P1, P2 cross V1 divided by the norm of V1. And of course, you could replace V1 by V2 if you wanted to, as long as you replace it on both the top and on the bottom. What about skew lines? That's lines which do not intersect and they're not parallel. So they do not intersect and V1 cross V2 is not the 0 vector. Now, there must be a point Q1 on the first line, which is closest to line 2, and there must be a point Q2 on line 2, which is closest to line 1. And then the distance between these two lines will be the same as the norm of the vector from Q1 to Q2. Now, the vector from Q1 to Q2 will be orthogonal to both lines. It will be orthogonal to V1 and it will be orthogonal to V2. We know how to get a unit vector which is orthogonal to V1 and V2. We'll just take V1 cross V2 and let's call that N for the time being. So the vector from Q1 to Q2 must be the same as the vector projection of the vector from P1 to P2 onto the vector N. In this picture, the vector N is round about here, something like this. We have a formula for the projection of a vector onto a vector. The norm of this is the absolute value of P1, P2 dot n divided by the norm of n. So the distance between skew lines must be the absolute value of P1, P2 dot V1 cross V2 divided by the norm of V1 cross V2. This is our formula. Now let's look at some examples. Before that, let me just very quickly recap. Intersecting lines, that's easy. The distance must be 0. If we have parallel lines, this is the formula we need to use. If we have skew lines, then instead we use a different formula. Find the distance between these two lines. Now I can tell you that these lines do not intersect. I haven't proved it here, but I'll leave it for you to check. These lines do not intersect. We need a point on line 1. We could take 0, 0, 0. We need a vector which is parallel to line 1. We can look at the numbers in front of the t, 0, -1, and 1, to get 0i minus 1j plus 1k. We need a point on P2. We could take the first numbers, 1, 0, and 0. And we need a vector which is parallel to line 2. So look at the numbers in front of the s, 2, 1, and -3. We can calculate V1 cross V2. And I'll leave it for you to check. This is 2i plus 2j plus 2k, which is not the 0 vector. So these two lines which do not intersect must be skew lines. Once we know that, we know which formula to use. We know that we need to use this formula. The distance that we're asked to calculate is the absolute value of P1, P2 dot V1 cross V2 divided by the norm of V1 cross V2. And I'm going to skip the details here. I will leave it for you to check my calculations. Please check that I haven't made a mistake here, and check that the distance between these two lines is 1 divided by the square root of 3. Let's move on to planes. This chapter is about lines and planes. So far we've been talking about lines. We also need to talk about planes. Imagine we have a plane in space. To describe this, we need two things. We need a point on the plane. Let's call this P0. And we need a vector which is perpendicular to the plane. We'll call this vector n. We say that the vector n is normal to the plane. Now, in this picture, we can think of the vector from P0 to P. And we can imagine shifting the vector n to just here. And then, of course, the angle between these two vectors must be 90 degrees. So the dot product of these two vectors must be 0. We use this as the definition of the vector equation for the plane. The plane passing through the point P0, which has normal vector n, has the vector equation n dot P0 to P is equal to the number 0. These two vectors must always be orthogonal. If we write this equation in terms of coordinates, that's the same as saying a multiplied by x minus x0 plus b multiplied by y minus y0 plus c multiplied by z minus z0 is equal to the number 0. Or we could rearrange this to the standard form, ax plus by plus cz is equal to d. where d is a constant. For example, find an equation for the plane passing through the point P0, normal to the vector n. We start with the standard equation, ax minus x0 plus by minus y0 plus cz minus z0 is equal to 0. And then we just put the numbers in. N gives us the capital A, B, and C. A is 5, B is 2, and C must be minus 1. From the point P0, we have x0, y0, and z0. x0 must be minus 3, y0 must be 0, and z0 must be 7. So we get 5x minus minus 3 plus 2y minus 0 plus minus 1 multiplied by z minus 7. Simplify that all out, and we get the answer 5x plus 2y minus z is equal to minus 22. This is the equation of a plane. Now, let me remark that the vector AI plus BJ plus CK is normal to the plane AX plus BY plus CZ is equal to D. So anytime we're given a normal vector and we're asked to find the equation for the plane, it's always going to be AX plus BY plus CZ is equal to some number. So all we're going to be doing is finding the number D. Or we could go backwards. If we're told a plane and we're asked to find the normal vectors, then we're just going to pick out the numbers. The number in front of the x, the number in front of the y, the number in front of the z. We'll use these to write down the normal vectors straight away. For example, find a vector normal to the plane x plus 2y plus 3z is equal to 4. We don't need the number 4. That's not relevant for normal vectors. All we want are the numbers 1, 2, and 3. So immediately we can write down, and then the normal vector is I plus 2j plus 3k. Find an equation for the plane containing the points E, F, and G. We have 3 points in the plane, so we can find 2 vectors in the plane. How can we find a vector which is normal to the plane? How can we find a vector which is orthogonal to EF and orthogonal to EG? We can just take their cross product. EF, I'll leave this for you to check, must be 2i minus k. EG must be 3j minus k. Take their cross product, and I'll leave it for you to check, must be 3i plus 2j plus 6k. This vector is normal to the plane. So the equation for the plane must be 3x plus 2y plus 6z is equal to some number. What is the number? We can use any point in the plane. Let's say we use the point 0, 0, 1. Put the number 0, 0, 1 into our formula, rearrange it, and we find that the number D, must be 6. So the answer is 3x plus 2y plus 6z is equal to 6. lines of intersection. There's two possibilities if we have two planes. Either the planes are parallel, that's the same as saying that n1 is equal to k multiplied by n2 for some real number n, and that should actually be a non-zero real number k. Or the other possibility is that the two lines intersect in a line. The two planes intersect in a line, called the line of intersection. They intersect if and only if n1 is not equal to a constant multiplied by n2. Or to say that another way, if n1 is not parallel to n2. Now, a vector which is parallel to this line must be orthogonal to n1 and it must be orthogonal to n2. How do we get a vector which is orthogonal to both n1 and n2? We can take their cross product. For example, find a vector parallel to the line of intersection of these two planes. We're going to find normal vectors, a normal vector to each plane, and then we're going to take their cross product. The first part is easy, just copy the numbers. From the first plane, the numbers are 3, minus 6, and minus 2. So the first normal vector must be 3i minus 6j minus 2k. And then again, for the second plane, the numbers are 2, 1, and minus 2. So our second normal vector must be 2i plus j minus 2k. And then we're going to take their cross product. Please check this calculation for me when you re-go through this and let me know if I've made a mistake. I think we get 14i plus 2j plus 15k, but please check that for me. This vector must be parallel to the line of intersection of these two planes. Find the point where the line given x is equal to 8 over 3 plus 2t, y is equal to minus 2t, z is equal to 1 plus t, intersects the plane 3x plus 2y plus 6z is equal to 6. So we have some plane, and we have some line which intersects the plane somehow. And we're asked to find the point where the line intersects the plane. This is straightforward. This is just playing with the equations. I'm going to start with the equation for the plane. 3x plus 2y plus 6z is equal to 6. And instead of x, I'm going to write 8 over 3 plus 2t. Instead of y, I'm going to write minus 2t. And instead of z, I'm going to write 1 plus t. There we are. Let's multiply everything out and simplify. And we end up with t equal to minus 1. The line intersects the plane when t is equal to minus 1. So the point of intersection is the point xyz when t is equal to minus 1. That's 8 over 3 plus 2t, comma minus 2t, comma 1 plus t, when t is equal to minus 1. And you can check that that's the point 2 over 3 to 0. the distance from a point to a plane. And again, that's the shortest possible distance between a point S and the plane. Now, the shortest distance, that's this one, which is written as D over here. I'm going to write it, draw it in orange. This line must be parallel to the normal vector n. So this distance must be the same as the projection of PS onto n. So we know this, we know how to do the projection of a vector onto a vector and then take the norm of it. The formula is absolute value of PS dot n divided by norm of n. I write that at the top. Find the distance from the point 1, 2, 3 to the plane x plus 2y plus 3z is equal to 4. We're going to be using this formula. So what do we need? We need a point in the plane and we need a vector which is normal to the plane. Those are straightforward to get. First of all, how do we get a point in the plane? We need a point x, y, z which satisfies the equation. And of course, there's infinitely many points on the plane, but we only need to find one of them. How can we make this easier for ourselves? We can make it easier for ourselves if we choose two of the variables to be 0. And it doesn't matter which two we choose. I might say x and y 0, or I might choose x and z to be 0, or I might choose that y and z to be 0. Here, I'm going to choose y and z to be 0. It doesn't matter which two, just choose two of them and make them 0. And then we're left with x is equal to 4. So the point 4, 0, 0 must be on the plane. Anytime you need to find a point on the plane, choose two of the coordinates to be 0 and then calculate the third point. We need a normal vector. That's straightforward. Clearly I plus 2j plus 3k. And then we use the formula. The distance that we're asked to calculate, I will leave this for you to check, should be 10 over the square root of 14. There's another example in the textbook, example 11. I'm not going to bother covering that in the class because it's just the same idea is repeated. But when you do your independent study, please read example 11 in the textbook. One final idea for today's lesson, the angle between two planes. I suppose we have two planes which intersect like this. What is the angle between them? Well, we can see from the picture that there's two angles that we could choose. We could have the angle theta, which is the same as the angle between n1 and n2, or we could have 180 degrees minus this angle. And the angle that we want is actually the smaller of these two angles, whichever one is smaller. More precisely, the angle between two planes is defined to be equal to whichever of the following angles is smaller. Either the angle between n1 and n2 or 180 degrees minus the angle between n1 and n2. That means that the angle between two planes will always be between 0 degrees and 90 degrees. Let's do an example, the final example of today's lesson. Find the angle between the planes 3x minus 6y minus 2z is equal to 15 and the plane minus 2x minus y plus 2z is equal to 5. We need the two normal vectors. We need to find the angle between the two normal vectors. We saw that in the last lesson. And then if that's between 0 and 90 degrees, we're finished. If that angle is more than 90 degrees, then we'll do 180 degrees minus that angle. So two normal vectors, that's easy. 3i minus 6j minus 2k and minus 2i minus j plus 2k. And then the angle between them, using the formula from the last lesson, must be approximately 101 degrees. That's not between 0 and 90 degrees, so what we do is 180 degrees minus 101 degrees. The angle is approximately 79 degrees. And that brings us to the end of today's lesson. Next week, we will move on to chapter 13. We'll start talking about functions of several variables, limits and continuity in higher dimensions, and then derivatives in higher dimensions, partial derivatives, and then the chain rule for partial derivatives. Do you have any questions?